The paper we are digging into today is called BabyVision, Visual Reasoning Beyond Language. And if you're short on time or just want the 1-minute version of why this paper is making waves, here's the key takeaway. So state-of-the-art multimodal large language models, MLLMs, have what the researchers call an inverted profile of competence. Just picture this. They can absolutely ace PhD-level benchmarks like MMMU, answering these super complex questions, but they consistently, and I mean catastrophically, fail at basic visual tasks. We're talking about things a 3-year-old can solve without even thinking. So to figure out what's going on, these researchers built the BabyVision Benchmark. It's a test of 388 questions across 22 different visual subtypes, all grouped into 4 critical categories like spatial perception and visual tracking. And the whole thing is designed to really minimize any reliance on language, forcing the models to use pure core visual skills. The results, well, they expose a massive capability gap. The top model they tested, Gemini 3 Pro Preview, only scored 49.7% overall. That is way behind the adult human baseline of 94.1%, and crucially, it's way behind the roughly 70% that 6-year-olds scored. The authors conclude that MLLMs just lack these fundamental visual building blocks, all because of something they call the verbalization bottleneck. Okay, so let's really unpack this.
Yeah, that inverted profile is really the core contradiction we're seeing in AI right now. We're building these models that can do incredible things with language, but they're failing at what seems like the most basic visual geometry. I mean, you have to ask yourself, if a model has seen literally billions of images, why hasn't it picked up on foundational common sense, like, object permanence or how to trace a simple line?
It just feels so counterintuitive, right? But the key insight here, I think, comes from developmental psychology. What's so important to grasp is that the skills BabyVision is testing, things like differentiating depth or tracking an object, these emerge in humans in the first few months of life. These are pre-linguistic skills. Our brains are figuring out the physical world long before we have words for it.
Precisely. We tend to forget that language is just a later layer, an overlay on top of this deeply structured visual understanding we already have. And when the researchers built this benchmark, they weren't just guessing. They were rigorously mapping these competencies based on developmental psychology textbooks and standardized visual tests. They built a whole taxonomy to pinpoint exactly what was missing.
Okay, so let's dig into the structure of the benchmark itself. You said 388 questions, which is a lot of data, and it's split into those 4 core domains.
And those 4 domains are absolutely essential because each one tests a different flavor of visual reasoning. The first one, fine-grained discrimination, sounds simple, but it's really punishing for these models.
Like a spot the difference puzzle.
Exactly, but one that's designed to defeat linguistic shortcuts. You've got subtypes like find the different, find the same, and reconstruction. It forces the model to look at the actual pixels, not just slap a semantic label on something.
And the second one is visual tracking. This seems so easy for us, just following a path.
For us, yes. But for a model, it means tracking continuous lines, complex trajectories. Think mazes, following tangled lines, or even navigating a metro map. The model has to maintain the identity of an object across a continuous space.
Then there's the third domain, spatial perception.
And this is so critical for any kind of 3D understanding. It's about inferring 3D structures from a 2D image. So you have these really mentally challenging tasks like count 3D blocks, figuring out paper folding, or imagining different 3D views. This is where you really start to see the models fail at physical simulation.
And the last one they test is visual pattern recognition.
Right, which is about identifying logical and geometric patterns, like rotation patterns or overlay patterns. It requires the model to treat visual elements like variables in a logical equation, not just as static images.
What's really fascinating, though, is how hard they worked to make sure the benchmark was actually valid, that it was really measuring vision and not just, language pattern matching.
Oh, the curation process was incredibly rigorous. They threw out any questions that relied on a lot of text or cultural knowledge or high-level semantics. And more importantly, every single final question included a detailed solution process.
A solution process? What does that mean in practice?
It means they made the human annotators write out the step-by-step visual logic needed to get the right answer.
So it's not just the answer is A.
Exactly. It had to be derived from visual analysis and spatial logic. They even had a double-blind expert review to make sure the test was, in a way, language resistant.
So let's talk about the cold, hard numbers, because this is where that inverted competence idea goes from a theory to, well, a pretty stunning reality.
That direct comparison is really the heart of the paper. You start with the human baseline, Adults are at 94.1% accuracy, super solid. And they test in kids at 3, 6, 10, and 12 years old. And that gives you this clear developmental curve. It shows you where this kind of grounded reasoning really starts to kick in.
And when you put the proprietary MLLMs up against that, the performance is, frankly, embarrassing. Gemini 3 Pro Preview, the best of the bunch, barely cracks 49.7%. Just think about that for a second. It's basically guessing on half the problem.
And the drop-off after Gemini is really steep.
Yeah.
You have GPT 5.2 down at 34.4%, Dubao 1.8 at 30.2%. But then you get to models like Grok 4 and Claude 4.5 Opus,
What were they?
down at 16.2% and 14.2%. I mean,
What?
that's getting pretty close to just randomly guessing on a multiple choice test.
So if you put those scores next to the kids' scores, most of these top-tier MLLMs are performing worse than the average 3-year-old. That's just staggering.
It is. Even the best one, Gemini, is still a full 20 points behind a typical 6-year-old. So it can pass an advanced chemistry exam, but it fails a kindergarten logic puzzle.
What does that tell us about what the models are actually doing?
It suggests that when they succeed on those high-level multimodal tasks, like, say, reading a complex medical scan, they're probably not understanding it spatially. They're likely using textual reasoning patterns to explain the image. It's a different process.
And if we drill down into a specific failure case, it gets even worse. You mentioned count 3D blocks.
That task was a complete disaster for them. It requires inferring hidden volumes, maintaining this 3D mental model, even with occlusion.
And the best score was what, 20%?
20.5% across all models.
Yeah.
That is a massive, massive red flag. It just screams lack of capacity.
So they just can't do that mental rotation.
They can't. They can't perform those mental-defined transformations. They substitute real simulation with description, and description is just not a good enough coordinate system for 3D space.
That is shocking. So is there a unifying theory for why they fail so badly, or is it just a bunch of different problems?
Well, this connects directly to the author's qualitative analysis, and this is where it gets really interesting. They found 4 systematic recurring failure modes, and they all seem to stem from the model's fundamental reliance on compressing vision into language. They think the MLLMs are almost structurally set up to fail these tasks.
Okay, so let's break down those 4 failure modes.
The first is the loss of fine-grained detail. The model just can't distinguish between options that rely on really subtle subsemantic cues. A slight difference in curvature, a few misaligned pixels. The model is forced to use semantic compression, turning that rich, continuous visual data into discrete text tokens. It's like turning a high-res photo into a really blurry, low-res JPEG. All the detail is lost.
So if you ask it to reconstruct a shape exactly, it'll just see a square or a curve, but it loses the precise fidelity of the line. The language layer is like a lossy filter.
Exactly. The second mode is the loss of manifold identity, which you see all the time in visual tracking tasks. This is where the model just can't maintain the identity of a continuous line or a path when it goes through an intersection or behind another object.
Whereas a human just sort of visually locks onto the curve and follows it.
Right, we use primitive contour integration, but the MLLM tries to map that continuous path into a set of discrete instructions, like go straight, turn left, go straight again.
And at a complicated intersection, that instruction list just breaks down.
It breaks, the model gets confused, it switches tracks, and it fails the maze because it doesn't have a persistent nonverbal idea of that specific curve's trajectory.
Okay. And the third failure mode?
Failure of spatial imagination. This is that 3D reasoning breakdown we saw with the terrible scores on the 3D blocks. The models just cannot perform the necessary mental transformations.
They substitute simulation with description.
Yes. They summarize what they can see and then try to infer other views based on linguistic rules. But language is linear and space is volumetric. This leads them to hallucinate impossible hidden shapes or just get projections completely wrong because they aren't constrained by a model of the physical world.
And the last one, the fourth mode.
Failure of visual pattern induction. So when they're tested on geometric or logical sequences, the models will often confuse some superficial attribute, like a color, with the actual underlying rule.
So it might fixate on a color changing instead of seeing the rule as rotate 90 degrees clockwise?
Exactly. It confuses the variable with the operation. It latches onto a spurious correlation instead of treating the objects like abstract pieces in a logical puzzle.
So if you tie all these failures together, the diagnosis seems pretty clear. It's the verbalization bottleneck.
That's the core idea.
Semantic content, like a description of a red ball, that translates just fine. But all those fundamental geometric relationships of the precise curves, the spatial positioning, what the authors call undescribable visual properties, all of that gets lost when you force raw perception through a language compression layer. The model's reasoning brain is only getting a low-fidelity summary of the image.
And that failure immediately raises the next big question. Can you just train your way out of this? So the researchers looked at whether a technique like reinforcement learning with verifiable rewards, or RLVR, could help.
And they did get an improvement, right? But it wasn't the fix they might have hoped for.
Right. The fine-tuning gave them a 4.8-point gain in accuracy overall. But when you look at where that gain came from, it tells you everything.
It was all in the tasks that could be reasoned about with language.
Precisely. The model got better at describing patterns or things that were already partially verbal. But the one category that relies almost entirely on nonverbal tracking, visual tracking, it saw little to no improvement. In fact, it had an overall loss of 1.2%.
So the reinforcement learning just couldn't reward the model for pure spatial insight because that insight gets garbled by the language layer.
It struggles, yeah. Which suggests that trying to fix visual reasoning by just tweaking the linguistic output is fundamentally the wrong approach. And that brings us to the most exciting part of the paper, I think.
The idea of bypassing the bottleneck entirely.
Exactly. Through visual externalization. This is the whole motivation behind BabyVision-Gen. It's a generative version of the benchmark.
So 280 near questions, but instead of a text answer, the model has to generate an image as the solution. It has to trace the path or complete the pattern.
It mimics how a human solves a maze, right? You trace it with your finger, you draw on it. You don't just stand there and narrate the directions to yourself. It forces the model to maintain that spatial coherence all the way through the process.
And how did the generative models do?
Well, the results are still pretty low, but you can see some promise there. A model called Nano Banana Pro got to 18.3% accuracy, which was the best of the bunch. But the core limitation of today's generative models became immediately obvious. Visual tracking is still basically an impossible challenge for them.
What was the score on the maze tasks?
0% across the board. On maze and connect the lines, a flat 0.
Wow.
It just shows this profound difficulty in maintaining spatial and structural coherence over a long generation sequence. The model can start a path, but it just can't execute the geometry needed to finish it correctly.
So if we connect this to the bigger picture for AI researchers, the finding seems to be that we need models that can reason in visual space, not just language space.
That's the direction this is pointing, towards these unified multimodal architectures, maybe models like Sora 2 or VO3, that integrate visual understanding and generation at a much more native level. The hope is that those kinds of architectures could maintain a high-fidelity visual representation throughout the whole reasoning process and completely bypass that brittle linguistic choke point.
So what does this all mean for foundation models? I think the main takeaway from this analysis of BabyVision is that MLLMs, for all their incredible achievements, are just structurally incapable of robust, grounded visual reasoning. Not until they fix this fundamental early vision foundation. Maybe we should be benchmarking them against kindergartners, not just PhD exams. Until they can trace a simple line, their claim to understanding the physical world seems, well, pretty questionable.
And this raises a really important question for you, the listener, and for everyone working in this space. If a large multimodal model can solve advanced physics problems, if it can pass medical board exams, but it cannot trace a continuous line through a simple maze without getting lost, can we really say it has a grounded, physically aware understanding of the world? Or is it just getting exceptionally good at optimizing a linguistic token stream based on massive data correlations? BabyVision gives us the diagnostic tool we need to start taking that question very, very seriously.